everyone, and welcome back. Today we're going to be continuing our exploration of multivariate statistical analysis and go over the basic principles that you definitely should know when it comes to conducting a multivariate ANOVA test. So what exactly is a multivariate ANOVA test? And some people will even call it a Manova test. So the goal of this is to test the null hypothesis that mu1 is equal to mu2 all the way down to mu g, where g is going to represent the number of groups that we're testing across. And the important thing about this test compared to our univariate ANOVA test is that each of these objects, mu j, belong to a d-dimensional space, right? So these are not numbers, these are all vectors. So we're testing the equality of a bunch of mean vectors. Right? So again, for semantic purposes, if D is equal to 1, so it's a univariate ANOVA test, some people will just call this an ANOVA. And if D is greater than or equal to 2, then some people also call this a Manova, or a multivariate ANOVA test. So let's first off go through the assumptions that need to be satisfied in order for the interpretations of this Manova test to be, potentially trustworthy. So the assumptions are going to be as follows. And these assumptions follow parallel to the univariate ANOVA case as well. So P1, P2, down to PG, the populations for which we're going to gather multivariate samples from, must all be associated to multivariate normal distributions, each of them having a mean vector mu j and some associated covariance matrix sigma j. Keep in mind, mu j is a d by 1 vector, and sigma j is a d by d matrix. So that's the first thing that we need. So each of these populations must be multivariately normally distributed. The second assumption that must be met for this Manova test to be trustworthy is that each of the population covariance matrices, sigma 1, sigma 2, all the way down to capital sigma g, must all be equal to one another, and usually we refer to this as multivariate homoscedasticity. So multivariate homoscedasticity. So all of the covariance matrices must be equal to one another. Most of the time we don't know this, so we would have to test this with some multivariate extension of, say, the Bartlett test, which is what we usually use for the univariate case. And thirdly, the third assumption that you definitely should have is that you should have independence of the observations within each of the samples, Sj coming from Pj. Right? So as long as you have these three assumptions, and some will even add a couple more just to have a little bit more statistical power associated to this test, then for the most part, all the assumptions, test statistics, and p-values that you generate from a Manova test should be relatively trustworthy. So, among all of these tests, the first one that you probably should test is multivariate normality, which we'll get into at another time in terms of how to test that. But you could, of course, look at the Mahalanobis distances, which you should know is associated to a chi-square distribution, and then calculate, say, a Mahalanobis quantile plot, and see if we have at least qualitative evidence to support multivariate normality. But the second test, in particular to the multivariate homoscedasticity, we can always use the box test, which I've briefly mentioned before, but let's just mention it again, and sort of represent the test statistic in some sense a slightly better way than we had before. So the box test, which I'm going to abbreviate as BO stat, since BA is going to represent our Bartlett, which is the univariate version. So this can be equal to n minus g, where n is the number of observations across each of our samples, g is the number of groups we're dealing with, and then we have our total degrees of freedom, which is just nu1 plus nu2 down to nu g, where nu j is equal to nj minus 1. And then it's going to be the natural log of the determinant of the associated pooled covariance matrix, and then we're going to subtract the sum from j is equal to 1 to g of our nu j times the natural log of the determinant of our individual covariance matrices for each of our random vectors. So this is the box test statistic, and as long as multivariate normality is satisfied, then this will follow a chi-squared distribution with the degrees of freedom for which I'm going to represent as VBO. So this degrees of freedom nu bow is going to be equal to 1/2 of d times d plus 1 times g minus 1. Now notice a nice little special case when d is equal to 1. Notice that we're going to have 1 times 2 divided by 2. That's just going to be 1. We're just going to have g minus 1, which is the degrees of freedom for the associated distribution of a Bartlett test statistic, i.e. the univariate case, right? So that's actually a nice little observation that you can make here. Right. Now, there is one slight downside of this box test statistic, especially if you're working in higher dimensions. So there's another test statistic that you might want to use to assess multivariate homoscedasticity, and I'm going to represent this as MBO for a modified box test statistic. So this is just going to be a modified box test statistic. Right? And all I'm going to do is I'm going to scale this new natural log determinant object by a different number, and this is going to take into account the dimensions that we're working in. Because if you look at the box statistic, you don't see any letter D here to represent the number of dimensions. So even as you increase D, this box test statistic doesn't really take that into account, aside from the degrees of freedom, which slightly takes it into account, but not directly. So what we can do is we can scale that natural log comparison, and the more appropriate scalar factor will be equal to n minus g again, and then we're going to have minus 1/2 d squared plus d, and that's going to be over the sum of 1 over nu j minus 1 over nu. And that denominator actually should look familiar if you remember your Bartlett test statistic. And then we're going to be multiplying this by our typical object above. So this is going to be equal to our new natural log of the determinant of our pooled covariance matrix, and then minus the sum of our individual nu j natural log of the determinant of sigma j. Right, so that's our same object, and again, this is a little bit more appropriate when you're working in higher dimensions, and again, this is associated to a chi-squared v bow test degrees of freedom, and this degrees of freedom actually stays fixed, which is actually pretty convenient for us. And let's just briefly write here formally what exactly this modified box test statistic does. So this is going to be better if the dimensions we're working on is arbitrarily positive. And let's sort of think about why we need to take even dimension into account. So this is because as the dimension increases, the probability of finding some difference, and some is subjective of course, but some difference between our sigma hat j's increases also, and that's only by chance, right? So the probability of finding differences increases by chance because we're increasing more matrices into our account, so our box test statistic needs to adapt for that. So when we actually do this, this is going to scale out what we're actually going to be comparing things to, and that's going to help us sort of take that into account, right? So if you're working in, say, dimensions 3, 4, 5, or maybe 50, you definitely should be using the modified box test statistic to assess multivariate homoscedasticity. Now that we've discussed the assumptions of the Manova test, now let's start to build our test statistics that we're going to use to assess the equality of these mean vectors. So let's briefly go over the metrics that we used in our univariate ANOVA test. So for one dimension, what we had was a decomposition of our total sum of squares into an error sum of squares and what we call a model sum of squares. And then from these, we divide each of those by their degrees of freedom and calculated an F test statistic to assess the equality across all of our means. So let's just briefly review what those formulas were for the univariate case. So the SST was equal to the variance of all of our observations multiplied by little m minus 1. The SSE was calculated by summing across all of our groups, so from j is equal to 1 to g, of our individual degrees of freedoms times our individual variances for each of these groups. And over here we have our SSM, and this was calculated by summing again across all groups, so j is equal to 1 to g, of that individual sample size times the mean of that individual sample minus the grand mean of that sample. So what we're going to try to do is generalize each of these formulas to a multivariate case. All right, so let's just briefly segue very slowly into that. So for d is greater than or equal to 2, what do we need to have? So if our random vector xj, and keep in mind this is equal to x1, x2 down to xj, and keep in mind this is j is equal to 1 to all the way down to g, then if we pull all samples, and keep in mind these are not just samples, but they are multivariate. So let's write multivariate samples together and create a what we call, or what we can call, a total vector. And let's call this total vector x is equal to x1, x2. Again, that's going to go down all the way down to xd, and that actually should be xd as well, and that's for the jth component. Then from this particular total vector, you can calculate a variance of this random vector, and we're going to be representing that as s sigma t. So this is going to be analogous to our SST, right? So this is going to be the variance of our total sum of squares matrix. Okay, so that's going to be our total sum of squares matrix. So instead of having our samples separated, so keep in mind we're going to have, for example, for sample 1, we're going to have a height, a blood pressure, and a happiness value. For sample 2, we're going to have a height, a blood pressure, and a happiness value. And those are going to be summed across, for example, n1 of those. We're going to have n1 of those. We're going to have n1 of those. And for our second sample, we're going to have n2 of those. We're going to have n2 of those. We're going to have n2 of those. And then what we're going to do is we're going to pull all these happiness values together, pull all these blood pressures together. We're going to pull all our happiness values together, and we're going to be creating some total vector, and that's going to be generating a associated covariance matrix, right? Because generally speaking, this is going to generate a covariance matrix sigma hat 1. This is going to generate a covariance matrix sigma hat 2. So what we need to do to pull these together, because we know that the total variance is not the sum of the individual variances, because they could be correlated with each other, is we need to pull all of them together to create a total sum of squares variance matrix, which we're going to denote as S sigma t. So if we have this, which is going to be analogous to our SST metric in the univariate analysis of variance case, then we also need two other matrices, which I'm going to denote as S sigma E, and we're also going to denote the other matrix as S sigma M. So this is going to be two other matrices that are going to be representing things parallel to SSE, and that's going to be associated to parallel SSM. Right? So that's going to give our SST is equal to SSE and SSM, but as matrices, and maybe they add together to give us our S sigma t matrix as well, which I'll also mention. So what are we going to define these matrices as? So if we want to define S sigma E matrix, and we want to define it analogous to our univariate case, what we can do is we can sum from j is equal to 1 to g of the degrees of freedom multiplied by that covariance matrix for that group, and that's obviously going to be a matrix. And keep in mind that's going to be analogous to our sum of nu j sj squared. And then for the other matrix, S sigma M, or SSM matrix, this is going to be equal to what? So if we want to build something similar to nj x bar minus x bar bar squared, we cannot square vectors, because x bar is going to turn into a vector, x bar bar is going to be another vector, and a vector squared is not typically well defined. So that's going to be turning into, for example, UTU or UUT, depending on the object that we're actually aiming for. So if x bar is a d by 1 vector, and we multiply that by the transpose of that, what is that actually going to be? So that's going to be a 1 by d object, right? But if we do x bar transpose times x bar, that's going to be a 1 by 1 matrix, or in some sense a scalar. So we want a d by 1 times 1 by d, so we need to do object times object transpose in order to get that particular matrix out. Multiplying it by nj is just going to give us a scalar version of that matrix, and summing up matrices will also be a matrix. So following that strategy, what we're going to do is we're going to sum, again, from j is equal to 1 to g of nj. And then we're going to do our x bar vector for group j minus x bar bar. And then we're going to multiply that by x bar j minus x bar bar transpose. Okay, so that's going to be our S sigma M matrix. And what is this x bar bar vector? So x bar bar, so this is going to be our grand mean vector. And this is going to be equal to the sum from j is equal to 1 to g of nj times x bar j vector divided by our total size m. Okay, so that's our grand mean vector. Right? So now that we have our matrices, is there any connection between these three matrices? And yes, there definitely is. Now this is not as easy of a proof as the univariate case, but this proof is definitely very beautiful. And it says that the matrix S sigma T can be decomposed as the sum of these two matrices, S sigma E and S sigma M. Right? So it takes this multivariate vector space and partitions it into these two disjoint vector spaces, S sigma E and S sigma M. Right? So now that we have these matrices that sort of follow a pattern to our univariate case, now we need our test statistic or test statistics if there are more of them. So how many test statistics are commonly used? There is definitely several many out there, including for the univariate ANOVA case, but I'm going to mention 4 of them that are commonly used. So 4 commonly used test statistics for a multivariate ANOVA case. So let's get right into these. So the first test statistic that I want to introduce actually might be viewed as the easiest to calculate, but keep in mind just because it's easy to calculate doesn't mean it's the most useful or the most practical or the most trustworthy. And this is called the Roy test statistic. So I'm going to be denoting the Roy test statistic as R stat. And the R stat is going to be defined to be equal to the maximum eigenvalue of the matrix S sigma E inverse times S sigma M. Right? So it's the maximum eigenvalue of the product of these two matrices. And you may be looking at this and you're like, why would I even care about this particular matrix? So if you remember, the F stat from the univariate case was defined to be equal to MSM all over MSE, which is just the SSM and the SSE matrix divided by their associated degrees of freedom. And if you think about inverses of matrices, which is just ugly notation for reciprocals if we're a fraction, this is pretty much like S sigma M over S sigma E. No, that's not what the inverse of a matrix is. It's not 1 divided by a matrix, but in some sense the formula hints at that type of structure. Right? But nonetheless, we have a square matrix inverted, and keep in mind the eigenvalues of those should be non-zero since it is a covariance matrix, so it is definitely going to be invertible. So we have an invertible square matrix times another invertible square matrix, which should be an invertible square matrix. So you should have a maximum eigenvalue of that square matrix, and it should be a real number as well. So once you calculate the maximum eigenvalue, those maximum eigenvalues are going to be associated to an F distribution of degrees of freedom D, comma, n minus g minus d plus 1. Again, D is the dimension that we're working under, and the total sample size, G the total number of groups, and that is going to be associated to an F distribution as long as homoscedasticity and multivariate normality are met. Now, it's just looking at the maximum eigenvalue, so it's definitely not going to be trustworthy, especially if you have a lot of outliers out there. Also, if it's not multivariate normal, this is definitely not going to give you anything useful. So the second test statistic that can be used is called the Pillai test statistic. So P-I-L-L-A-I. So the Pillai test statistic, which I'm going to be denoting as P-stat. So P-stat is going to be defined as the trace, so the sum of the diagonal entries, of the matrix S sigma E plus S sigma M. So the sum of those two matrices inverted multiplied by the matrix S sigma M. Some people will also call this the Pillai trace test statistic. So now we're looking at the sum of diagonal entries, which is almost like the sum of eigenvalues. So we're not just looking at the top, now we're looking at the sum. And one can show as long as multivariate normality is met, this is also going to be associated to an F distribution with slightly different degrees of freedom. Degrees of freedom being D, G minus 1, and then N minus G plus 1. Right? So what is so advantageous about the Pillai over the Roy? So this test statistic, one can show theoretically, is useful if the assumptions are, and I should put here, slightly not met. Because in some sense it's theoretically still premised on multivariate normality, but if you have some doubts on multivariate normality or homoscedasticity, then the Pillai definitely is going to be a little bit more useful than the Roy. Okay, so the third test statistic does a little bit more better than the Pillai. So the third is called the Wilks test statistic. So the Wilks test statistic, which I'm going to be abbreviating as W stat, is going to be defined to be equal to N minus G minus 1/2 D plus 2 times the natural log of the determinant of S sigma T all over the determinant of S sigma E. So here we go, we're comparing the determinants of two covariance matrices, taking the log of it. So it's hinting at that max log likelihood type of estimator, sort of like Bartley and Box was going for. So if it takes that particular structure, and since Bartley sort of has the same exact motivation, you would probably guess that this is associated to a chi-square distribution, and if you guess that, then indeed you would be right. So the Wilks test statistic, and some people will also call this object the Wilks lambda value, this interior of this natural log. Also, some people look at the reciprocal instead. But I'm just going to keep it as is. This is going to be associated to a chi-squared degrees of freedom d g minus 1. Okay? Now, some people will even change this scalar a tad bit so it follows an F distribution, which is going to be a little bit more robust if your sample size is smaller, right? Or again, if you have doubts on the assumptions that you're dealing with. So another Wilks test, which I'm going to call the MW step, or the modified Wilks test statistic, can be defined as N minus G minus D plus 1 all over D times G minus 1. So this is just going to give us a different scalared value. So think about what's going on here. So as the dimension increases, this test statistic is going to decrease. So it sort of takes into account the same exact motivation as the modified box test statistic for multivariate homoscedasticity, right? Which can be useful because we don't want that by chance variation to be affecting our analysis of data. So once we have that scalar done, that's going to be multiplied by, again, the natural log of the determinant of our S sigma T matrix divided by the determinant of our S sigma E matrix. Right? So same little natural log quotient, and one can show that as long as multivariate normality is met, then this is going to be associated to an F distribution with a degrees of freedom pair of D G minus 1, so the same as the chi-square degrees of freedom, and then comma N minus G minus D plus 1. So it's the same secondary degrees of freedom as the Roy test statistic, and almost the same as the Pillai test statistic without taking into account the dimension of the data, for the second part at least. Right? So that's the Wilks test statistic, and this modified test statistic, and this is good or better, I guess you could say, than the original. So better than, at least on average, the W stat if the sample sizes are smaller. Right? But if you have larger sample sizes than the original W stat, we'll do just fine. So that is the Wilk and the modified Wilk test statistic. And there's one more that I think deserves to be mentioned, and this is the Hartelling. The Hartelling test statistic, which is the same Hartelling as the the paired and the unpaired and the unpooled two covariance matrix test. So for the Hartelling test statistic, which I'm going to denote as H stat, this is going to be defined to be equal to the trace of the matrix S sigma E inverse times S sigma M. So if you look at this test statistic and one of the other test statistics, in particular the Pillai test statistic, it's still looking at the trace of a particular matrix. And let's actually put them next to each other. So let's look at the Pillai test statistic and the Hartelling test statistic. So we have the trace of S sigma E plus S sigma M inverse, and then we have S sigma M here. Right? So what's the difference between them? So this actually is looking at the SSM over the SSE, which the Wilk naturally wants to do. And also the Roy test statistic looks at the same exact matrix, but instead of looking at the maximum eigenvalue, the Hartelling test statistic looks at the trace of that particular matrix, which is the sum of the eigenvalues, which is a subset of the maximum eigenvalue. And for this, the Pillai test statistic looks at the SSE versus the SSM added together, which, keep in mind, SSE plus SSM is the S sigma T matrix. So this compares SSM over SST, and the Hartelling and the Roy looks at the SSM over the SSE metrics, which is actually very, very interesting, right? So they're looking at different quotients of matrices. One's looking at the total, and one's looking at the SSE matrix, right? So very, very interesting observations there, but you can sort of see how they're motivated and manipulating one another. So the Hartelling test statistic, if multivariate normality is met, is also going to follow an F distribution with degrees of freedom D, G minus 1, N minus G minus D plus 1. So it's actually the same exact degrees of freedom as the modified Wilks test statistic, right? And this test, the Hartelling, is going to be good if our sample sizes Ni and Nj are not equal to one another. Okay, so the Pillai, and let's mention this here, Pillai is actually good if Ni and Nj are equal to one another. And you might not remember why equal sample sizes are actually good for a ANOVA test, because you remember from the univariate test, if our sample sizes are equal to one another, which we usually call a balanced design test, the statistical power for that particular test is actually optimized. So it's actually going towards that particular realm of theory. Right? But those are four test statistics: Roy, Pillai, Wilk, modified Wilk, and also Hartelling, that are used to test the equality of mean vectors, as long as they come from populations that are multivariately homoscedastic and also multivariately normally distributed. So, hope you enjoyed this video, and I'll see you in the next one. Take care.